Ciao, ciao a tutti. I apologize for the delay.
Yeah.
Ciao Lee.
So, are you okay now?
Yeah, I'm ready to start.
Okay, so I would like to make a brief introduction before you start. Okay.
Yes, of course.
And can we make a recording for the lecture?
Yeah. Yes, sure.
Okay.
I think he's already started because
Okay. Yeah.
we are already recording the lecture, I guess.
Yeah. Các em sinh viên sẵn sàng chưa? Chúng ta bắt đầu được chưa các em?
Dạ rồi thầy.
Okay. So, hello everyone, and good morning, good afternoon, Professor Alessandro Bosisio from Italy. I should say good morning in Italy, right?
Thank you. Yes, of course.
So first of all, on behalf of the Faculty of Electrical Engineering, I'm very pleased to welcome Professor Alessandro Bosisio and would like to say thank you so much for your lecture with our students today. The topics you are going to share with our students in the field of renewable energy and renewable integration into power system today and next Sunday. They are very useful to our students because this energy resource is attracting a lot of attention in Vietnam. Yeah. So now it's your time, please. Again,
Okay.
thank you very much. Yeah.
Thank you very much. Thank you very much, Professor, and I'm very happy to be here with you all, and also with you, my friend. And thank you also from my side for this invitation, for being here and try to. I would not say to teach, but to share what I studied, what I researched in the last years. Okay, so basically, what I would like to share with you is something related to power systems and renewable energy sources. So sometimes many students or researchers are focusing just on RES. Okay, so the way we can produce electricity from wind, from sun, from waves, etc. But there is sometimes a lack in studying or in understanding the impact of renewable energy sources on the power systems. Okay, so in these two lectures, today and next Sunday, I will try basically to give you some information to give you an idea of the challenges that we are facing and we will have to face in the near future. Okay, to integrate renewable energy sources in the power systems. Okay. I apologize from the beginning because I introduced some slides at the beginning. So today basically it will be a lecture a little bit more general on the power systems, But you will see that I also included many interesting information about RES and power systems. So it is not just to let you know how the power system are made, which basically I guess you know already, but to show you how the power system is made historically, let's say, and which are going to be the changes and the challenges that the traditional power systems has to face to integrate as much RES as possible. Okay. So let me share the screen. Okay, but can you hear me very well? Can you hear the audio well?
Yeah.
Okay. So before starting the lecture, we will start the lecture with a video. So we, in a few seconds, we will be back to the end of 80s, okay, when the electricity start to be spread around, okay. I don't want to come back to let's say ancient time, but this video is very interesting, and I will let you know later why it's interesting also for us. I just want to say a few words about myself. So basically, I studied in Politecnico di Milano. You probably know this university because also Professor Duong did his PhD in Politecnico from 2011 to 2015. Then I had a postdoc position till October 2020, where I became assistant professor in Politecnico. And 2 weeks ago, I would say, more or less, I got a position as assistant professor tenure track in University of Pavia. Pavia is a city very close to Milano. And basically my main research interests are in distribution system operator and planning, power system optimization, and of course the operation of renewables and smart grids. My really main focus is on distribution network because I work for a long time, basically since the starting of my PhD, with the DSO, the distribution system operator of Milano, which is called Unareti. So I took a little bit, I would say, much experience in distribution system operator, and based on that, I will also show you at the end of this lecture what is, in my opinion, a very interesting thing. So I will show you in reality, okay, how the distribution network of Milano is made. Okay, you will be very surprised to see how it is complex, and you will discover that having the electricity in all our households is not a game. Let's say it's something very challenging, and again, having a RES connected to the power system makes these challenges also more challenging. Okay, but basically, let's start with this 10 minutes video. Let me know if you can hear the audio. It should work, but if you cannot hear anything, just let me know. And then we will be back here to discuss a little bit the content of this video. So this video basically presents the so-called war of currents. I don't know if you hear about this war that basically happened. It is not a, let's say, war in which they use weapons, let's say, but was a war that basically decided if our power system will be or would be done in AC or DC. Okay.
Have you ever wondered what was inside that electrical socket, or how electricity came to be? Most people think Thomas Edison was the inventor of all things electric, but many people do not know that there was a great debate over how to power the world, and it became the first standards war. What we know today as electricity is powered by an invention of Nikola Tesla and George Westinghouse, two big players in the battle to electrify the world. Thomas Edison was born in Ohio in 1847. He liked to tinker, was interested in chemistry, and was fascinated with electricity. As a full-time inventor, he had many patents, improved the telephone, and invented the phonograph, which was one of his greatest inventions. After the phonograph, he started to become more interested in electricity. He saw that gas lamps used for lighting homes were too unreliable because they smelled and sometimes caught on fire. He began to work on a new system to power homes. He developed a system that he called direct current, which was a flow of charged particles that moved from a positive to a negative terminal, creating electricity. After developing direct current, Edison invented the incandescent light bulb and began working to build the first DC generator. He built a DC generator to power the business district of Pearl Street in New York, and in September of 1882, switched 59 new customers to DC power. Within the next few years, Edison expanded his system to several cities, creating 18 central stations in the U.S. Around the same time, another inventor and entrepreneur, George Westinghouse, was trying to introduce his own current to the world. George Westinghouse was born in New York in 1846. At a young age, he was interested in mechanics because his father was an entrepreneur working with machines. After the war and attending college, he noticed that the main form of transportation, railroads, were very unsafe. It took so long for them to break that a speeding train took 2 miles to stop. Westinghouse developed a new braking system called the air brake. The test run was successful, stopping just in front of a buggy on the tracks, and the air brake established Westinghouse's success. Later, he noticed that railroad signs powered by gas were problematic, so he went on to create his own electricity company to help solve these issues. After reading an article on the AC system, he decided to seek the help of Nikola Tesla, an immigrant electrician and inventor. Nikola Tesla was born in 1856 in Serbia. He went to college in Austria and had a great interest in electricity and mechanics. While in college, his physics professor brought in an Edison DC motor to show the class. Tesla observed the motor and saw that there were too many parts that rubbed together, and that it could easily break. Tesla had thoughts of a motor that was spun by a rotating magnetic field. He told his teacher about his ideas, only to have them rejected. One day in the park, however, an ingenious idea struck him, and Tesla began drawing the AC motor in the dirt. Alternating current is two currents that alternate very quickly, giving it twice the strength that direct current has. AC had a clear advantage over DC because DC needed big and heavy copper wires to get a charge over a long distance. With AC, electricity could be sent over a great distance at high voltage, and then the transformer could decrease the voltage when it got to the home. In 1884, Tesla came to the United States to work with the famous inventor Thomas Edison. Tesla worked with Edison for less than a year, and then left after a payment dispute. Edison did not like the idea of alternating current, knowing that AC and DC could not work together. Tesla felt that alternating current was a more effective current, and continued his work on his own. In 1888, Tesla received several patents for his AC motor. Soon after, Tesla was contacted by Westinghouse, who purchased all of his patents. Tesla then began working alongside Westinghouse to apply his AC motor to Westinghouse's system. The battle of the currents began with the fear of electricity. When the blizzard of 1888 hit, many telegraph wires fell because of the weight of the snow, killing 2 people. Edison saw this as a chance to take the lead in the race to defeat AC and to save his DC system. His DC system was not as powerful, so it did not harm people the way AC could. He had scared people enough so that they didn't buy the AC system. To increase fears, Edison called in Harold Brown, an electrical engineer that worked for him and was also against alternating current. Newspapers were filled with headlines about how dangerous electricity was, so Brown decided to perform animal experiments with electricity to show that DC was not as harmful as AC. Edison agreed, so they tried 1,000 volts of DC on stray dogs, showing that the dogs were still alive and unharmed. Then they tried just 300 volts of the AC on the dogs, and they fell over stiff and dead. They continued experiments with other animals, and by this time, the experiments were open to the public, so they could see the deadly effects of AC. People were shocked by the torturous demonstrations. Edison also knew that people could die from electricity and felt that the method of executing criminals was outdated. He made the first electric chair and, of course, chose AC to power it. The first criminal that chose to die by electricity was William Kemmler in 1890. Kemmler's lawyer, Bort Cochran, thought to be paid by Westinghouse, tried to convince the courts that AC shouldn't be used.
There then ensues this long drama of Cochran constantly challenging and appealing the use of electricity, saying that this would be cruel and unusual punishment because no one could really guarantee that Kemmler, in fact, would be killed on the first effort. And
when they sent the AC current through him, he didn't die immediately, and the voltage had to be increased in order to execute him. Edison decided to call electrocution being Westinghouse. The AC current now had death written all over it. Edison and Brown then tried to convince the state legislature to ban AC current from use. Westinghouse knew that AC was a much better current than DC, so when the time came to enter exhibits into the Columbian Exposition in Chicago, he wanted to show the world the AC system. He had already supplied an alternating current system to the Colorado mining town of Telluride, and it was very successful. The world was starting to notice the benefits of AC power. Westinghouse Electric entered into a bidding war with Edison's former company, now the General Electric Company, to power and light the fair, and won. Furious, Edison refused to allow Westinghouse to use his patented light bulb, so Westinghouse made his own two-piece light bulb to light up the fair. On the day of the fair, Westinghouse turned on the generators and the fair lit up. Everyone was amazed at the light show. They had an exhibit for the alternating current, and it showed how the current worked. Edison also had exhibits at the fair, but it just showed most people how outdated the DC system really was. Tesla held demonstrations at the fair that astounded the public, including one in which he was surrounded by 200,000 volts of alternating current and seemed to glow. By the end of the fair, Edison's DC had clearly lost the battle. Lord Kelvin, one of the leading physicists of the day and a DC supporter, had warned in a cable in early 1893 to avoid the gigantic mistake of alternating current. After the fair, however, Kelvin was completely convinced of AC's superiority, and his commission granted Westinghouse the Niagara contract. In 1895, Westinghouse decided to prove AC's power with one of Tesla's dreams. Tesla always wanted to go to Niagara Falls and thought that it would be a great place to have a power station run by water. He imagined a wheel in the waterfall that spun with the water. The wheel would generate power for the houses around the falls. They had to install 3 AC generators at the top of the falls for it to work, but once the generators were installed, they supplied houses in Buffalo with AC power. The generators gave power to people within a 200-mile radius. In spite of the success at Niagara, Edison had one last-ditch effort to discredit the AC system. In 1903, he performed another animal experiment, this time with an elephant. He recorded it on a motion picture camera that he had just invented. The elephant, named Topsy, was a temperamental circus elephant that had killed 3 people and was to be executed. Edison proudly stepped up to the task and said that he would kill her with 7,700 volts of AC. To prove once again that AC was dangerous, he electrocuted the elephant while a crowd of 1,500 watched. People were horrified by the event, but because AC had already been established in many homes, the event quickly faded from memory. The battle was finally over, and Westinghouse and Tesla came out victorious with their AC current. The AC-DC Battle of the Currents was a success. because it led to better technology, a more productive society, and it was the beginning of our modern world. It led to inventions like batteries, remote controls, and radio. It also led to a more productive society because the dishwasher, washer, dryer, and microwave were all invented as a result of this battle. It was the beginning of our technology-based world because it was the start of a new era full of light and power.
Okay. So the video was quite rude, okay, but it is also interesting and also in the nowadays transformation of the power system, okay. So did you catch from the video which was the weak point of the DC with respect to AC? So you saw that Edison try in all the ways to say that AC was bad and dangerous. Okay, so also using some experiments on animals and also humans, unfortunately. But finally, which was the main drawback of DC? Someone was able to catch it from the video? Can you hear me?
Yes.
Okay. So basically, which is the magic, let's say, I would say magic machine of AC, is this guy here, the transformer, okay? Which, as you know, just works in AC, okay? So if you supply a transformer in DC, it's not going to work, okay? So basically, the main problem of DC is basically that was, I would not say not, sorry. I would not say is, but was, and I will come back to this difference very soon. The direct current was not easy to be converted from higher to lower voltages, okay? So basically, if you want to transmit power over long distances, okay, there was the example of Niagara Falls, and that they were able to carry power and energy 2 miles far away, but with the AC, not with the DC, okay? Because with the DC, the conversion, so the increasing of the voltage and the decreasing of the voltage was not very easy. While on the other hand, with AC, this transformation, basically, it is very, very easy. Keep in mind this, because in the next slides, you will see many transformers, okay, that sometimes we take as given, okay, something that we have since the beginning, and it's something very, let's say, stupid machine, very easy, very reliable, but basically it is very important in the power system, okay, because without a transformer, you would end up with the same issues of the DC, okay? It's a very fundamental and important machine, electrical machine. So finally, there was this war between Edison and Tesla, and at the end, the AC won over the DC, okay? And as you probably know, nowadays, the power system are almost all in AC, alternating current, not direct current, okay? But there is always a but, because nowadays, even if the electricity is powered in AC, many appliances like computers, LEDs, and also power generators like PV power plants are in DC, okay? And moreover, there are some methods available for converting the direct current to higher to lower voltages. So basically now we have something available and cheap, which makes something similar to what is made by the transformers, okay? So basically, if we have to build a new power system right now, maybe the DC would be even convenient than AC, because as I said here, the customers, so the appliances, and also the generation of electricity, especially from RES, is in DC, okay? So while you have to convert from DC to AC and then back from AC to DC, it is better just to have a DC power systems, okay? So basically, it seems that after more or less 100 years, okay, the war of currents may not be over yet, okay? But basically, maybe in the future, we will have a parallel operation between DC and AC, so a sort of hybrid armistice, okay? And I will be back also to this collaboration between AC and DC power system in one of the next slides, okay? So what about electricity? As you hear also in the video, electricity was really disruptive at the beginning of 90s, okay? Because it gives us the possibility of growing, of improving our life and our way of producing and our way of moving around, okay? So it was was a revolution, I would say. And nowadays, the electricity is an essential service, okay? So you can imagine that if you will end up tomorrow with no electricity, you will not be very comfortable, okay? You will not be able to light your house, or you will not be able to keep your food and beverage cold. You will not be able maybe to take the underground, and maybe you will not have water in your house because the pumps will not work, okay? So basically, the electricity nowadays is an essential service. And since it is an essential service, basically is also a political sensitive issues. I don't know if you know what is happening in Europe right now, and especially in Italy, due to the war between Ukraine and Russia. We are facing a very big issue related to the price of electricity, okay? So you have to imagine that, for instance, in 2020, during COVID, the cost of electricity in Italy was around, let's say, 40 euro megawatt hour. Now in 2022, it costs 4,000 euro by megawatt hour. So basically 10 times more. That's very dramatic for factories, but also for normal people. Let's say, let's consider to your bill, your electricity bill was 50 euro a month, let's say. Now maybe you are paying 500 euro a month. It is not like that, because the price of the bill, the cost of the bill is not just the energy price, but just to give you a reasonable number, let's say, you have to multiply by 10 the cost of the electricity bill you were paid just 2 years ago. So you can imagine that many people and families are facing very big issues to survive, okay? And now, since we are entering winter time, the same is for the gas, okay? Then we will have very tough months. This is just to let you know that I don't know the situation of Vietnam, but be very careful. Don't do the mistake we did in Italy. Just to have more or less one fuel used for producing electricity. You know that in Italy, almost 70% of the electricity comes from gas, okay? And from the gas come from Russia, right? So since the European countries now are fighting Russia, the price of gas increased a lot, and also the price of electricity. The mistake of Italy is here in this percentage. So you cannot rely the production of electricity just on one fuel, which is gas, and especially from one fuel, gas, and one country, Russia. So this is a very, let's say, the perfect storm, okay? Because if you are losing Russia, you are losing gas, you are losing electricity, which is an essential service, okay? So I don't really know the situation of Vietnam. Probably you know, or for sure you know better than me. But please, since probably you will be, you know, the guys that will guide also the politicians in this, try not to be, I will say, as stupid as we have been, and try to make to have a mix of technologies, okay? A mix of technologies. So in this very tough situation, of course, even Italy is now pushing a lot on RES, okay? Because basically, which is one of the advantages of RES, is that they don't need fuel, or the fuel is something that you have already on your territory, okay? Because if I install a PV power plant or wind power plant in Italy, I will use, let's say, the energy comes from the sun, basically, which does not belong to anyone, okay? It's free. It's freely available. So just this gives the opportunity not to be dependent from other countries, okay? The drawback, unfortunately, is that for having RES, you should have some materials like silicons and stuff. So if you don't have this material, you are more or less in the same position of we are now. But basically, if you assume to have the rest installed, at least for the fuel, you are safe. Okay, because if the sun is not shut down, you have sun, so you have solar and wind and all the other renewable energy sources. Another thing that you have to keep in mind when you are focusing on RES is that the electricity cannot be easily stored. So the delivery of the power, of the energy, has to be practically instantaneous. So the generation and demand are permanently imbalanced. So that this is a very is one of the main concepts of the power system. So if you are generating something, you're generating electricity, you should have a demand, or vice versa. If you have a demand, you should have the same generation always. Okay, this has to be right always. Okay, but you know for sure that RES are really unprogrammable, right? What does it mean, unprogrammable? You cannot say to a solar, a PV power plant to increase the production. You can say to this power plant to decrease the production, but not to increase. Okay? You cannot say to a wind power plant to increase the production, because if you do not have wind, you cannot have electricity from wind. And the same, if you do not have solar, you cannot have electricity from a PV power plant. So basically, one of the main issue of the RES, and we will speak longer next Sunday, is the fact that are unprogrammable. Okay, which is one of the main difference than a thermal power plant. Because in a thermal power plant, up to the installed capacity of the power plant, if you get more fuel, you get more electricity. If you get less fuel, you get less electricity. And in this way, you can follow the demand with the generation. But that's not the case of RES. Okay? For RES, if you are producing something, you should find a way of using this electricity or store this electricity. But as you see here, store is not easy. Okay? And we will back to this concept later on. Okay? The third characteristic of electricity is that to supply electricity, you requires networks. Okay? Because basically you have the generation side, the demand side, but you have to put those two sides in contact. How you do that? Using some networks. Okay? And basically the network duplication does not make any economic sense. So the network are basically a natural monopoly. Okay, what does it mean, natural monopoly? That building networks is very, very, very expensive. So, and it doesn't make sense to have a duplication. Okay, so you don't have in the same area two transmission lines that maybe belong to two different companies that are fighting each other. You just have one network, one company. It doesn't make sense to duplicate the networks. And some other, let's say, characteristics that are not very special. So for having electricity, you need large and dedicated investments, okay? The electricity is also a measure very well the richness of a country, okay? If you want to see if a country is rich or not, just have a look to the penetration of electricity. The more the electricity is used and is spread, the more the country most probably is a rich country, okay? Because having electricity for everybody needs large and dedicated investments, okay? And it is also very complex because basically you have to make very large and dedicated investments, but you are not very certain. You have many uncertainties which are related to the deployment of the demand or the changing in the power productions. So you have to have big investments in a very uncertain framework. Okay, that's not very good for an investor. So, which is the structure of the power system? I will go a little bit faster because I know that your background is in electrical engineering, or it should be in electrical engineering. But just to be all on the same wave, basically the power system is mainly divided in the following subsystem. The first part is the generation. Okay, in a traditional power system, so I would say traditional, you have a very big power plant, okay, which are producing electricity in medium voltage, okay, so I would say 10 kilovolt. Then when the electricity is available, which is the first thing that you have to do? You have to increase the voltage using a transformer, okay? So here you have the power, okay? Why we are increasing as soon as possible the voltage? Can you help me? Why we have to increase the voltage as soon as possible? Just after the power plant. Do you have an idea?
To decrease power loss.
To decrease power losses, right. So the power, we could say that is proportional to the voltage and current, okay? And with the transformer, you can play with the ratio between voltage and current, okay? So you can increase the voltage to decrease the current, or vice versa, you can decrease the voltage to increase the current. So basically, since we have to transmit the energy, the power produced from the power plant over normally a long distance, and since the Joule losses are proportional to the square of the current, if we increase with the transformer the voltage, we decrease the current, so we decrease the Joule losses very strongly, okay? So to have a power system more efficient, the transformer is the magic machine I told you already, okay? Because it gives us the opportunity to transmit power over a long distance without having a very high Joule losses. This is very important also for a concept that I will let you know later, related to RES in Italy, especially. So once I increased, okay, the voltage, okay, so here for instance, I increase from 10 kV to, for instance, 380 kV. So in Italy, the extra high voltage and the high voltage system are at 380 kV and 150 kV, I would say. Okay. Probably in Vietnam you have other voltage levels, but basically look from 10 kV to 380 kV. What I'm doing is to decrease by almost 40 times. Sorry. You are decreasing the current by 40 times. Okay. So basically, if on the power plant side you have, I don't know, let's say 40 ampere, okay, on this side you just have 1 ampere, okay. You can imagine that putting here 40 versus 1, it makes a big difference in terms of power losses, okay. So the energy, the power that will flow here will result in a very low power losses, okay. That's the goal of the transformers in the power system. So the energy goes from the power plant to the transmission network, and then the energy enters what is called the primary substation. So in primary substation, we have another transformation from high voltage to medium voltage, okay. So here you go from medium voltage to high voltage, and here from high voltage to medium voltage. Someone of you knows why the closer we are going to the final users, the lower we get the voltage level. So why we don't get to the final users using 380 kV, so that we have lower losses? Why the more we are going to the final users, the lower is the voltage, which is the ratio? Do you know an idea? Is for technical issues, for security issue?
Because it's safer and we need our wanted to use. Yeah.
Okay, so it is just for safety reasons, no? Because you can imagine if someone wants to entering your house with 380 kV, okay? Since you are electrical engineering, you will keep this guy outside your place, no? Okay, and say you are crazy, no? So basically, the more we are going to the final users, the more we have to reduce the voltage level for safety reason. But that's also acceptable in terms of power losses, okay? Because basically a transmission line could be also 100 kilometer length, while the medium voltage line maybe are, let's say, 2 kilometer length, okay? So even if here, for instance, 150, let's consider to have a medium voltage line of 50, it means that I increase by 10 times the current, right? So here, if I have my 1 ampere, right? Here I end up with 10 ampere, okay? It is just an example. I just take this number to have a feeling of the number, okay? Of the numbers. So if here, instead of 1, I have 10 now, I will increase for sure the power losses. But basically, it's not a big issue because the power line is just 2 kilometers, not 100 kilometers, because the longer is the line, the more is the power losses. finally. Okay. So basically, in primary substation, and I will also show you in detail how the primary substation is made. There is another transformer. Okay, so look, the transformer is always there in the main point of the power system, and from the primary substation, some medium voltage lines start up to what is called secondary substation. Okay, this is a pole mounted secondary substation, but basically here you have another transformer. Okay, so TR1, TR2, TR3. So from the generation to the final customer, you have at least 3 transformers. Okay, so you have to imagine that the electricity that comes to your place has been transformed at least 3 times. Okay, up and down in terms of voltages and current. Basically, in the secondary substation, there is a conversion between medium voltage and low voltage. Okay, so let's have a look to the current again. So from, I would say, 15 kV to 400 V. Okay, so in Italy, the low voltage lines are at 400 volt 3 phase or 230 volt 1 phase. Okay, so basically here from 15,000 volt divided by 400 volt, you increase by almost 40 times the current. Okay, so basically, instead of having 10 ampere, okay, you will have 400 ampere. Okay, so just take this number as an example, of course. But basically, instead of having 10, I will have 400 ampere. But that's not an issue, because the low voltage lines are maybe long, like, I don't know, 500 or even less, let's say 200 meter. Okay, so even if you have a very high current, you have to distribute this current just over a very short distance. Okay, so the Joule losses are acceptable. Okay, so the fact of increasing the voltage here, it is not just for the losses, but also for the cross section of the cables. Okay, cables or overhead lines, because the lower is the current, the lower could be the cross section, so it is more economical. Okay. What about the load? You probably know that loads can be connected to all the voltage levels. Okay, they could be connected. Look here, to the high voltage side. So normally those are power factor. Okay, very big factor that maybe are producing, I don't know, steel or something that requires a huge amount of energy. Of course, here you will have for sure another transformer, or maybe 2 transformers, from high to medium, from medium to voltage. And then you have some industrial customers connected directly to the medium voltage, and also some commercial customers. And normally the residential customers are connected to the low voltage network. Okay, so the bigger you are, so if you are a customer, the bigger you are, the higher level of voltage you will be connected. Okay, so here you have to imagine to have a transformer here. Okay, from medium voltage to low voltage, but this transformer normally belongs to the customer itself, not to the DSO. Okay. So the company that runs the transmission network is called TSO, Transmission System Operator. The company that is running the distribution network is called the DSO, Distribution System Operator. Okay, those are the two entities in charge of the power system. Okay, so this is basically the structure of the power system. I said at the beginning, a traditional power system. Okay, why a traditional power system? Because in the in the nowadays power system, the transmission and the distribution it remain more or less the same. What is strongly changing is the generation. Why? Because we are facing the installation of distributed generators, especially from renewable energy sources, directly connected to the medium voltage, or also, okay, if I imagine here to have a PV power plants on the rooftop of this house, so RES connected to medium voltage and low voltage side. Okay, we also have some RES connected to the high voltage side. Okay, so maybe I can have let's say a solar power plant connected to the high voltage side. But which is, in your opinion, the most challenging situation? The PV connected to the high voltage, to the medium voltage, or to the low voltage side of the power system? So which is the more challenging situation? For sure is not the high voltage. Why is not the high voltage? Because look, the transmission network was made already to host some generation. Okay, so the only difference is that now I don't have maybe a gas power plant or coal power plant or nuclear power plant, but I have a PV power plant. But basically, I'm already used to have power plants connected to the high voltage system. What is very new is to have generation connected to the medium voltage or to the low voltage side of the power system, which completely change the operation of the distribution networks. But we will be back to this concept in the next slides. Okay, so this is just the power system in a more schematic form. Okay. So I don't want to waste time on this slide, but maybe the only novelty is here. This is the case of Italy. In Italy, the transmission network is managed by just one company, which is called Terna, that is running the power system from the big, let's say, I would say here, big generation plants to the primary substation. Here are primary substation. What about the distribution grids? Basically, in Italy, we have more or less 130 distribution system operators. So while the TSO is unique in Italy, the DSOs are many, more than 100. Okay, I don't know in Vietnam, but probably will be very similar. And look, this is one of the main challenges for distribution grids right now. So the integration, the including let's say the integration of distributed generators, especially from renewable energy sources, okay, which are not connected here, but are connected here, much closer to the final customers, okay. But which is the main difference? The main difference is that are not connected to the transmission network, but to the distribution network. A network that was not designed, the distribution grids were not designed to host distributed generation, okay? Let's imagine to add here another generator, right? Not from gas, but from PV. Do you think this transmission network will have many issues in hosting this new generator here, even if it's from PV, so from solar energy and not from gas? Basically, we are just changing the fuel, but the way the transmission network is planned and operate, it doesn't change so much, right? That's not the case of the distribution network, because the distribution network was not designed to host renewable energy sources. So it is in the distribution network where we have the main issues to be faced to move from traditional fuels to renewable energy sources, okay? So basically, just to very quickly recap, the goal of the electricity grid is to take the electricity from the generating units and bring this electricity passing through the transmission and distribution systems to the load. Okay, so basically the grid put in contact the generating units and the load. The transmission network, which is meshed, I will come back to this term later, is at higher voltage and it is used for long distance, while the distribution network, which is radial, okay, it is just for local distribution, okay. So the two parts of the parallel system are transmission network, meshed, high voltage, long distances, distribution network, radial, lower voltage, local distribution, okay. And the final goal is to bring electricity from the generation to the load. So what I would like to do now is to go into more detail of the load side, distribution network, transmission network, and generation units. Okay. Let's start from the load. This slide, it's it is very dense of information. I will try to explain you all. I don't know if you know this website here. This website is available from the Italian TSO, Terna, and if you have time, it is in English, so it is not in Italian. You can navigate it very easily, but it's very interesting because Terna makes available many data that you can also download it. You can also download from the web. Many data regarding the load, the generation, and the transmission network of Italy. Okay. And one of the information you can download is the daily or also the yearly load profile of Italy. Okay, so this is the load profile for Italy. Okay, here you see I just selected one day, the 25th of February 2021. So it's let's say winter time. And here you have the daily, okay? So here you have 12 a.m. midnight, and here you have 12 p.m. Okay, so basically here you have more or less 6 a.m. and here 6 p.m. Okay, and someone of you can help me in saying the difference. So why here we have a red line but also a blue line? Do you have an idea? So why we have two curves? The Italian load is one, okay? So why we have two different trends? Do you have an idea? So why, which is the meaning of the red curve and which is the meaning of the blue curve? Please, can someone help me?
The blue line the total load in Saturday, but the orange just the forecast in total load.
Yeah, that's the answer. Thank you. So basically, as you probably know, Turner every day makes a forecasting of the following day, okay, which is the red curve, okay. Then basically, look, I took this data between 9 a.m. and 12 p.m. Okay, so maybe here was 11 a.m. And basically, the blue line is the real, the current, the actual load profile, which for sure is a little bit different than the forecasted one. Okay. As you can see here, the two trends are very similar because, as you probably know, forecasting the load is quite easy. Okay, so it's not very difficult to forecast the load, or at least is easier than forecasting the production of wind or solar. Okay, so nowadays many researchers and also me and Professor Duan, we made some studies in forecasting, for instance, the wind production. Okay, because one of the challenges is the forecasting of renewable energy sources. Okay, but for the load, basically, let's say the behavior of people, it's more stable than the behavior of wind and solar. Okay, so the weather is more changing. It changes more than the behavior of people. But in any case, the red line and the blue line are not the same. Okay. And that's quite normal, but look, you don't have a very big difference. So the TSO has to change a little bit the schedule power generation, because you know that the TSO made the schedule of the power generation of the day ahead, okay, using the red curve, and then in real time it will change a little bit the production of the power units to follow the load, because you know that nowadays is the generations are the generators that are following the loads. Okay, so the red curve is given, or the blue curve is given, and we have to give this electricity using the generation. Okay. So apart from this detail, here you can see a very common trend for a day in Italy. So basically, look, you have a very strong ramp in the morning when the people wake up and all the activities restart. And then you have a decreasing in central hours of the day, okay? And then you have another increase in the evening when the people are coming back home, okay? And then another strong decreasing when people are going to sleep, okay? So this is, I think that probably it's quite the same also for Vietnam, because that's, you know, that the electricity gives also many information about the behavior of people, okay? So if people wake up, do something in the morning, then here, you know, is the lunchtime, and then you come back, and then you go for sleeping, and then so the load decrease for summer night, okay, for night hours. The minimum value is around, let's say, 2 a.m. in the night, okay. But apart from this concept, okay, I would like to highlight you to put your attention on two information, okay. So you basically this is Italy, of course, and Italy is basically divided in some bidding zones. So for the electricity market purposes, Italy is divided in some zones. So the north zone, the center north zone, the center south, the south, and then the Sardinia Island and Sicily Island. Okay. And here basically you have, for a given day, more or less the consumption in gigawatt hour of each of the bidding zone. Okay. As you can see from here, almost 60% of the energy is consumed in the northern part. Okay. So basically 60% of the energy is consumed in the northern part. Why? Because basically here is where all the factories and production is located, okay? Especially in the region where I'm living and where the Politecnico is, which is the region called Lombardia. Here, basically, you have most of the activities that are consuming electricity, let's say. So basically, 60% of the electricity is demanding here in the north. Okay, that's clear. And then some of the energy in the center north, center south, and just few here below. I would say 2, 4, 5, 6. Let me make a computation. 6 divided by 380. Let's say here we are consuming more or less 50%. Okay. So there is a very huge difference between the northern part of Italy and the southern part of Italy. I think it is quite the same also in Vietnam. Vietnam is a long country as Italy in terms of latitude. So the latitude of the northern part is quite different than the latitude of the southern part. Okay. Also here in Italy, the latitude here is very different than the latitude here. Okay. So basically, the load is in the north. Okay. Let's say load is located in the northern Italy. And what about the generation from RES? Okay, so that's the tricky point. This map here shows the kilowatt hour meter square, okay, of Italy. Since the latitude is very different, look, in the south, in the north, you can have like 1000 kilowatt hour meter square, while in the south you have 1800 kilowatt hour meter square. Okay, so if you are an investor, okay, so put the shoes of an investor, and you have to decide where to install a PV power plant. Where you would be happy to install it? Please help me. You will install it here, or you will install it here? What's your idea? It is better to install PV power plants in Lombardia in the north or in Sicily in the south?
Yeah, in the southern.
In the south, okay. While because basically you have more energy, okay. So the sun give you more energy. So with the same power install, you will produce more electricity, okay. So let's say that I would be happy to install a PV power plant in this area here, okay, where the solar radiation is between 1500 and 1800 kilowatt hour meter square. Okay, I would like to give you to tell you the same for the wind speed. Okay, so here you have the same map, but having the information about the wind speed. Okay, so if you were an investor, you will be happy to install wind speed in the north or in the south. What's your answer?
It's in the south.
Still in the south. So let's do something like this, okay? So here basically I have between, let's say, 5 and 8 meter second, okay, of wind speed. Okay, so I'm very happy for that, because if I install a PV power plant here, I will produce enough electricity to recover my investment. Okay, I'm very happy. But which is the problem? So the load is in the north, and let's say the RES production is in the south. So do you think this is good or bad?
It's not good.
Yeah, that's not very good. Okay, why is not very good? Because the best approach is to have the generation as close as possible to the load. Okay, but in this case, for the case of Italy, and that's one of the issue we are facing with the transmission network, is that basically most of the production from RES is in the south, but most of the load is in the north. So here you have the load, and here you have the production. So basically, we have to bring all this energy, all this power from the south to the north of Italy. So basically, we have to invest so much in transmission networks that bring the electricity from the south to the north. So let's consider that from here, from 1 to, let's say here, 2. From point 1 to point 2, we have more or less, I would say, 1,200 kilometers. Okay? So basically, you have to, that's just an example, but you have to build transmission lines long more than 1,000 kilometers. Is a huge distance. So even if you increase the voltage a lot, so you reduce the current, you still have joule losses, which are not, let's say, forbidden. Okay. While nowadays, but nowadays using traditional power plants make the possibility of installing power plants, I don't know, from gas or from oil or from coal, much closer to the load, because you don't need to have wind or solar for producing electricity. You just bring gas or coal or oil, and you can install the power plants much closer to the load. Maybe you just need to install them closer to a river or where you have water, but you have less constraints on the installation of thermal power plant rather than the rest power plants. Okay. So this is one of the issues we are very facing. So it's very nice to have RES. Okay, we like to have them. We like to go through a low carbon economy, let's say. But if you think just about the return of the investment related to the installation of RES, and you don't care about the infrastructure that has to bring the energy, the electricity produced from RES to the load, you are missing more, and you are missing a very important thing, that the electricity is finally bring to the final users. Okay, you don't just have to produce electricity, but you have to bring this electricity to the final users. Okay. So in this case, it would be better to have the production in the north or the load in the south. Okay, that's the idea. I think this is clear, no? It is a, let's say, geographical problem. Okay, you cannot choose where you have more solar or wind. So basically, you have to find a way to bring this electricity from the place where it's better to produce it to the place where you have the load, or you have to move the load closer to the generation, but that's not very easy. You can imagine. You cannot say to someone that has a factory in Milan to move this factory to Sicily just because you can produce electricity from PV or wind. This guy will tell you that you are crazy. Okay, and that's correct. So here, I just want to tell you something related to the load again and to the variability of the load through the week. Okay, here you have 1 week from Monday to Sunday, And basically the load normally varies over 5 days, which are more or less the same, okay, from Monday to Friday. And then you have Saturday and Sunday, okay. So from here you can catch many interesting information. Let's start from the forecasting issues. Look, Monday is much complicated to be forecasted rather than, for instance, Thursday. Look, Thursday has been forecasted very well from Turner, while Monday was not very well forecasted. Okay, while basically because here, you know, on Monday the people restart all the activities after Sunday, and maybe, you know, the schedule can change week by week. Okay, while Thursday is a little bit better, and then Wednesday and Thursday, you know, the activities are on the way, let's say, and basically the forecasting by Thursday is easier. What about Saturday and Sunday? Saturday and Sunday has a completely different trend. Look, the evening peak is higher than the morning peak, which is not the same as during the other 5 days. So the morning peak is higher than the evening peak. During Saturday and Sunday, the evening peak is higher, because here basically you have a more residential load, here a more industrial load. Okay, so here more residential, and here you have more industrial. Commercial. Okay, so here I just wanted to show you that the load is very variable. So the load varies. Okay, also you know for sure, and I will also show you later, that also the rest varies. Okay, and which is the result? The result is that you sum up, let's say, two uncertainties. Okay, so you have the uncertainty of the load, you have the uncertainty of the rest production. So you sum up those two uncertainty, and you end up probably with a huge uncertainty that you have to face with your power system. Okay, because as I told you, the load at the beginning, the load has also to be equal to the generation. Okay, in a traditional power system where you don't have RES, but you have traditional power plant, you don't have uncertainty on traditional generation, because, as I said already, the more fuel you give, the more energy comes from the power plant. Okay, so basically you can control, you can program the traditional power plants. So basically you reduce the uncertainty. So you just have the uncertainty of the load you have to cover with the traditional power plants. Nowadays, if we start increasing the RES, you have the uncertainty of the load, the uncertainty of the generation. You end up with a very difficult situation in terms of planning and operation of the power system. Okay, so the operation of the power system becomes much more complicated. Okay, So it is not just a problem of finding the place to install wind or solar. It is not just a problem of having wind, but it is also always a problem also of the power system. Okay, because the power system is in the middle between load and generation, and has to be operated by someone. And the more is the uncertainties, the more is complicated to operate the power system or to operate a system in general. Okay, so just to make another example, if you are driving your car on a highway, maybe United States highway, which is just straight, okay, it is much more easy than driving a car in a mountain path where you have many curves, let's say. Because on the highway, you can also be, let's say, you don't have to be aware in each second, okay? You can maybe also listen to some music or speak with your friend. But if you're driving in a very curvy road, you always have to be aware, because the uncertainties are much more, and if you are not aware, maybe you end up with an accident. Okay, the same is for the power system. The more I know what is happening the day after, the year after, in the medium long term, the easiest is to plan and operate the power system. Okay, but rest are unpredictable, and they vary a lot, so they are more difficult to be operated in the power system. Okay, so that's the concept you have to have in mind. Okay, so this is just a quite easy concept. So is the load duration curve. So if you take the demand, let's say the hourly demand of the load, for instance, for Italy, and you order the load from the highest value to the lowest value, you can end up with what is called the load duration curve. Okay, where basically you have some information about the shape of your load. Okay. So this lower part, which is called base load, okay, is the load that you are sure you have to supply for all the hours of the year. So you know that the years have 8,760 hours, okay, hours in a year, okay. So from this chart, you know that for all these hours, you have to supply more or less 18,000 megawatt. Okay, so this is your base load. In each hour of the year, you have to guarantee to have let's say 800 gigawatt. Okay, so normally, which are that's a question for you. Which are the power plants that are used for the base load? Nuclear power plant, gas power plant, renewable energy sources. Which are the power plants normally used? So the traditional power plant used for the base load, for instance, is the nuclear power plants. Why the nuclear? Why the nuclear power plants are very nice to cover the base load? Do you have an idea? You know that power plant, the cost of power plants are capex, so capital expenditure, and opex, operational expenditure. Okay, so the capex is basically the cost of building, the cost of installing the power plants. The opex are the cost of operating the power plants, so the maintenance and the fuel. Okay, here is, let's say, installation, and here are the operation, let's say the fuel. Okay, so a nuclear power plants have high capex, low opex, or low capex, high opex. What's your idea? So it is costly to build a new nuclear power plant, or it's quite cheap? So a nuclear power plant it's costly or not?
It's not. It's cheap.
Now, basically, to build a nuclear power plant from scratch, it's very costly. So for a nuclear power plant, the capex are very high. Because you have to build this power plant that has also to stay if an aircraft fall down on it. So you have infrastructure very costly. Okay, but then the fuel, so the opex, it's very cheap. Okay, so the capex are high and the opex are low. So why it's good to use nuclear power plants for the base load? Because basically, once I invested my money to build the power plant, the more I can produce electricity from it, the more I'm happy. Okay, because the fuel is very cheap. So I need to use this power plant as much as possible to recover the high capex cost. Okay, so we don't have nuclear power plants in Italy. I will let you know later why. But for instance, in France, they have nuclear power plants that they use for the base load, and that's a very nice option. Okay. And what about RES, renewable energy sources? Let's say solar and wind. What about the capex and opex of RES? The rest are more or less like nuclear or not? So high capex and lower opex or not?
Excuse me, Professor. You stop sharing screen. Yeah.
Sorry?
Sorry, Professor. I think you stop sharing the screen.
I stop sharing the screen. Let me check. Sorry, maybe it was a problem with the connection. Can you see the screen now?
Yeah.
Yeah, I see it.
So my question was, RES are like nuclear, so with high capex and low opex, or vice versa? Which is the cost of the fuel for a solar power plant? So which is the fuel of a solar power plant? Can you help me? Which is the fuel? So the fuel basically is the solar radiation, okay, which is free. So for RES, the OPEX are very, very low, because once you have installed your PV power plant, you basically do not have to invest any other money. Okay, so just the maintenance, but the fuel is for free. The solar radiation comes almost every day, and with the solar radiation you can produce electricity. So basically the RES, as the nuclear, has a high capex with respect to the opex. So also RES can go here in the base load, right? Because once I have installed my PV power plant, it's very useless if I don't produce electricity when I have solar radiation, right? When I have energy from the sun, I have to convert as much as possible this energy in electricity, okay? So basically the RES has always to be in production, has also to produce electricity once they have the fuel, which is for free, okay? While, for instance, a gas power plant is normally used, for instance, in Italy for peak load. Why gas is used for peak load? Because the OPEX of gas, so the cost of gas, especially in this period, is higher than the CAPEX, okay? So I need money to build the gas power plant, but I need less money than nuclear power plant with respect to the cost of fuel that I have to spend every time I'm producing electricity, okay? So based on the type of power plant I have, I cover the base load, the medium load, peak load, and also the reserve capacity. So it is always better to have a mix of technologies, okay? Because some power plants are good for the base load and some other for the peak load, okay? Just to conclude with the load, okay? This is an example of the load curve, of the yearly load curve of Italy in 2018, 2019, and 2020. Here it is just to highlight, if you look to the red rectangles, you could see very clearly this is April 2020. You can see really the decreasing, okay, the decreasing of the Italy consumption due to the lockdown, okay? So in March 2020, the Italian government decided to close all the activities. People have to stay home, and look the effect on the electricity demand, okay? So the electricity is always a measure of the people behavior, okay? I think this slide is quite interesting, basically. Okay, so before starting the generation part, I propose you to make like 10 minutes break, just to refresh a little bit. So we can be back at 10:30, okay, and continues with the presentation. Is it okay for you?
Yes.
Okay. So see you in 10 minutes, more or less. Okay, I think we can start again. If you have questions or doubts, please just interrupt me. I didn't tell you at the beginning, so don't worry. As I told you, I just want to share my experience, my research. So if you have doubts or a curiosity, just interrupt me. So don't worry, anytime you wish. So let's back to the presentation, and let's back to the second part of the power system, so the generation side. Okay, so up to now we have seen they say the four parts of the power system, and then a focus on the load. Then I would like to jump to the opposite side of the power system, so to the generation side. Okay, and then we will finish with the transmission and distribution networks. So what about generation? So for generating electricity nowadays, we have plenty of options. Okay, many technologies. What I called sometimes traditional power plants are the thermal power plants. Okay, so the thermal plants are nuclear, coal, oil, gas, both open cycle and combined cycle, and which is one of the main difference between those thermal plants is the fuel. Okay, so in a coal power plants you use coal to boil water, and then with the vapor you make the turbine rotating, and then the turbine make the synchronous machine rotating, and you can produce electricity. Okay, the same is for gas and oil. You have to boil water, and for doing that you use a different fuel. Okay, and this is the first group of power plant. The thermal plants are programmable. Okay, just try to keep this concept in mind. So are programmable in terms of I can increase or decrease the electricity production, just increasing or decreasing the fuel I'm using. Okay, of course you have an upper bound and the lower bound. The upper bound is the power installed, the lower bound is the technical minimum. Okay, so for instance, if you have a power plant of 100 megawatt, you can produce at maximum 100 megawatt and maybe at minimum 10 megawatt. Okay, there is normally a technical minimum you have to guarantee, otherwise you have to shut down the power plant. But in general, you can program, you can schedule how much energy you want to get from the power plant. Okay, the second group are hydro plants. I would also call the hydro plants traditional. That's not a mistake. Also, the thermal power plant are traditional. Because as you remember also from the video we watched at the beginning, one of the first power plant was an hydro power plant on Niagara Falls. Okay, So the hydropower plants are historically connected to the power system, okay, as for the thermal power plants. So even if sometimes the hydropower plants are included in renewable energy sources, basically are a little bit different, you know, because are in place since a long time ago, since the beginning of the deployment of electricity, basically. For the hydropower plants, we can define three types of plant. With the reservoir, which is what is reported in this picture here, run of the river, and pump storage. So to be honest, this is an hydro pump power plant. Let's start from the run of the river. So the run of the river, it is basically an hydropower plant that uses the flowing of water to move a turbine which is connected to a synchronous machine and finally to produce electricity. Okay, so you don't have a dam. It is not something close to what you see in the figure on the right. You just have maybe you can have a small dam, but basically you just use the flowing of the water. So you convert the energy of the flowing of the water in electricity. The second type is the hydro plants with reservoir, which is the one showing in this picture. So basically, in this case, you have two reservoirs, the higher and the lower, okay? And then basically you have a dam. So with the dam, you create the first lake, let's say, from where you take water normally in some pipelines, okay, and use this water to move the turbine, which is connected again to the generator that produce electricity that goes to the power system. Okay, of course you have the usual transformer, etc. Much more interesting, especially for us, is the hydropower plant with a pump storage. What does it mean, pump storage? It means that the turbine, it is not just a turbine, it's a turbine, but also a pump, okay? So can do both. Basically, when you want to produce electricity, you use the power unit has a turbine and a generator, and you inject power into the power system. Vice versa, when let's say you turbine water from high to low. Vice versa, if you want to pump water back from low to high, you consume electricity, and using a motor, you pump, okay, you pump water from below to up, okay. So basically, this is the ancient way of storage electricity, okay. So nowadays we are always, if you say storage, you most of the people think about electrochemical batteries, okay, but we don't have to forget that storage systems are installed in the power system since a long time ago, and our hydro pump power plants. Okay. So what is happening now in Italy? I'm working with a company which is called Edison, which is trying to install new hydro pump storage plants that has to work coupled with renewable energy sources. Okay, because one of the problems of RES is that they are not programmable. I told you this word many times. So sometimes maybe the production of RES is higher than the load demand. In that case, it could be nice to use the extra electricity from RES to bring water from down, from here, one to here, and then to use back the water to produce electricity when the load demand more electricity. Okay, so it's a storage system as batteries. Okay. And then we have the last group of power plants, which are the renewable energy sources. So wind, solar, thermosolar, photovoltaic, fuel cells, geothermal, biomass, wave, etc. Okay. So nowadays, the power system is supplied by a mix of these technologies. Thermal power plants, hydro, which are the traditional ones, and then some renewable energy sources. So up to now, most of the energy still comes from thermal and hydro, but the renewable energy sources are becoming more and more. Okay. Just another concept. Basically, as the thermal power plants, also the hydro power plants are programmable, or are quite easy to be programmed. Okay. While the rest are not programmable. You have energy when wind and solar, just to be general, are available. So you cannot say to the sun, tomorrow you have to give me more solar radiation. Okay, that's impossible. And here, back to one of my first concerns regarding the energy situation in Italy is why it's good to have a mix of generation technology. There are at least 3 reasons. Economic reasons, and here we are back to CapEx and OpEx, okay? So sometimes, for instance, for the base load, it's better to have a power plant with high fixed and small variable cost, while for peak load, it's better to have a power plant with small fixed and high variable cost. So having a mix of power plants, so a mix of thermal, hydro, RES, could help, could be the most economic approach, okay? So saying that a power system with 100% of RES is more economic than a traditional system, I would not say that. Okay, I don't have the numbers, but I will be care about saying something like that. Okay, maybe it's better for environmental reasons to reduce CO2, but in terms of being more economical than the current power system, I would not say that, to be honest. Then the second reason of having a mix of generation technologies is for strategic political reasons. So a fuel diversification is always good. Okay, so this is something that in Italy was not followed. Okay, you cannot base all your production of electricity only on gas. That's a very big mistake. Okay, so you have to have a mix of resources so that if a source, if you have a lack in one of the sources, you can switch to another source. Okay, and then environmental reasons. Because different generation technologies have very diverse environmental impacts. For instance, an hydropower plant do not create CO2 emission, but you have to install the power plants on the river, so you have an let's say environmental impact in terms of viewing or in terms of changing maybe the flowing of a river, etc., but not CO2. On the other hand, if you have a gas power plant, you have CO2, but maybe you can install this power plant in a place where the impact on the surrounding area is much less. Okay, so having a mix of generation technologies can help also in not impact too much one aspect or another one. This is a very, in my opinion, very interesting picture of the evolution of production and the type of power plant for the case of Italy. Okay, so this chart starts in 1963. Why 1963? Because in 1963 the power system was nationalized. So in 1963 the company Enel was founded, was settled by the Italian government, and the generation, transmission, distribution were all in charge of a single state company, which is called Enel. Okay. Look, in 1963, of course, look, the load, so the production is increasing through the years. Okay, if you look to the bars of 1963 and the bars on 2017, you see that we are at least 6 times more of power demand. Okay, so the increasing said there was a very huge increase in the electrification of the end uses. Okay, but back to 1963, look, most of the energy was from hydro. Okay, and then we had also a part of thermal and some geothermal power energy. Okay, so basically at the beginning of, let's say, not at the beginning of the electrification, but when the power system was nationalized, most of the energy came from hydro and thermal power plants. Then what happens? Look at the blue bars. The production of hydropower plants, which is different year by year because it depends on the availability of water, so rainfalls and when these rainfalls happen, etc., is more or less the same. Okay, this means that basically, at least in Italy, we used as much as possible the water available in rivers and lakes. Okay, so we can invest, of course, again in hydropower plants, but probably we are still using most of the availability for this source. Okay, then the power plants that increased much during the years are the thermal power plants. Okay, so look also in 2017. 2017 still most of the power in Italy is from thermal power plant, especially, I would say, gas. Unfortunately, I would say gas power plants. Okay, this trend is increasing by years. Then look in 1964. There was also a bit of nuclear, okay, which increased a little bit. But look here, what happens in 1987? May you guess what happens in 1987? Do you have an idea? Do you know what happened in 1986? Probably you are a little bit too young, but do you know what happens in 1986 related to nuclear? I was born in 1986, so I was a child, but at least I was already here. In 1986, there was the Chernobyl accident. I don't know if you have you ever heard about Chernobyl accident? The explosion of a thermal power plant in Chernobyl, which is now in Ukraine. Have you ever heard about this?
No.
No? Okay, so basically was a, let's say, dramatic event where a nuclear power plant located in the ex-Russia, okay, explode, and basically we were all affected by some radiations and things like that. Okay, so nothing very dramatic, but was for the public, let's say, feeling was a very strong event. So if you have time, I advise you to search on Google Chernobyl accident. And for Italy in particular, this was a dramatic. It was even a more dramatic event. Why? Because the government in 1987 set up a referendum where they ask to the citizens if they want or they don't want nuclear power plants on the Italian territory. You can guess after the Chernobyl accident which was the result of this referendum. The result was that most of the citizens said that they didn't want to have nuclear power plants in Italy. Even if basically we are surrounded by nuclear power plants in France, Switzerland, Germany, but the government or someone that was in the government at that time maybe was against nuclear power plants, and they set up this referendum just after this dramatic event, and the results is that in 1 year we completely shut down nuclear power plants. And what's the consequence of that is that nowadays most of our electricity comes from gas because we dismiss completely nuclear power plants. And due to the fighting between Russia and Ukraine, now we are in a very bad situation in terms of cost of electricity. If we would have at least a bit of nuclear here, maybe our situation nowadays could be better. Okay, but the story is like that. What about RES? RES basically started more or less in 1992. So basically it is 30 years, right? It is 30 years while RES were installed in the power system. Okay, so it's quite a long time, no? Let's say it's almost half of the time between the nationalization and 2017. Okay, but look, at the beginning, due also to the fact that the PV and wind technologies were very costly, etc. We had to wait till more or less 2008 to see the RES appearing in the mix of production. Okay. So basically, we could say that is more or less, let's say, 2008 to 10, like more or less 15 years of deployment of RES. Okay, but it's still a quite long time, no? 50 years, and you see that in just, let's say, 50 years, basically there was a very strong increase in the production from RES, which is more or less equal for 2017 to the hydropower plants. So it's a good, let's say, good results. But if someone says that Italy has many RES power plants, etc., now you can answer, yes, you produce some energy from RES, but look, the most of the production, more than 50% of the production is still from gas. Okay, so you don't have to be so happy. Let's say you invest money in RES, you install many power plants, but basically the production is still just a small part of the whole production, at least in Italy. Back to the impact of RES on the power system, okay, which is one of the consequences of having more RES in the power system. So you should know that renewable energy sources, at least in Italy, have what is called priority dispatching. Okay, so basically, if you have a RES power, this concept was introduced to incentivize the deployment of renewable energy sources. So if you have a RES power plants and you are producing electricity, in order not to waste it, you have the priority of dispatching. Okay, so you don't have to let's say, to be aware of there is someone that wants this electricity or not. All the energy from RES is taken from the power system, and to cover the load are the thermal power plants that are changing their production, okay, because are programmable, while RES are not programmable. So not programmable, the system get as much as possible. Programmable, I change the output to meet the load. Okay, but which is the consequence? The consequence is that from 2018 to 2020, the energy produced from thermal programmable generation decreased by 6%, while the energy from non-programmable RES increased by 12%. Okay? So this should be, and it is good. It means that wind and PV are producing more. So I'm reducing CO2 emission, etc., etc. But on the other hand, the guys that are running thermal power generation are not very happy. Why are not very happy? Because are using less, are producing less, so are getting less money. Okay. So one of the impact of RES is that the more RES we have, the more non-programmable RES we have, the less programmable generation we have. Okay. And having something not programmable, it's not the same that having something programmable for the operation of the power system. Because having something non-programmable makes the power system in a more critical situation. Because if you have a problem, if wind and solar suddenly disappear, and you don't have enough traditional power plant to recover this lack of production, probably you will end up in a blackout. That's what happened also in California a few years ago. Okay, if you just rely on solar, just think to have a power system that just relies on solar production. If in a certain hour of the year you have a cloudy day, probably you will end up in a blackout. Because if you cannot control the load is still demanding the same, but the generation completely disappeared, so you have a blackout. Okay. So the effect of having less programmable generation for sure make the power system more stable. Okay, it is more difficult to manage it, and it is more stable. It is less stable. Okay. This this slide is even very interesting in my opinion. I just try with these two figures, two charts, to show you the season's effect of the RES production. Okay, so the variability of the RES production. If you think about a thermal power plant, you do not have any correlation between the production and the season. You can produce the same in winter time, springtime, summertime, and autumn. Okay, because if you have the fuel, which does not depend on the season, you give fuel to the thermal power plant, and you can get electricity. For renewable energy sources, for sure, you know that there is a season effect. Okay. So hydro, wind, and PV, okay, biomass and geothermal are not really correlated with season, but hydro, wind, and PV are very correlated on seasons. So if you look to, those are real data for Italy. If you look to this chart here, you see the gigawatt hour, so the energy produced by geothermal, which is this light blue line here. Look, it's quite constant. Okay, why is quite constant? Because the heating of the earth is quite constant. Okay, if you make this power plant working, it will give you the same energy all around the year. Okay. Then you have biomass. Even biomass, it's quite stable, with just a small increase in summertime. But basically, even here, if you give fuel to the biomass power plant, you will get back electricity. What about hydro and PV and wind? Let's start from wind. The wind, you probably know, it's higher in winter time and lower in summertime. Okay, so you have more production from wind in winter time and autumn and spring, and less in summertime. Okay. Vice versa, what about hydro and PV? For hydro and PV, you have something different. So you have less production for winter and spring and autumn, and the highest production in summertime. So for PV, it's quite easy to be understood, because in springtime and summertime you have more solar radiation, so you have more production from PV. For hydro, maybe it's less easy to be understood, but at least for Italy, what happens that it happens that during winter time, the snow remains on Alps and Apennini, which are the two mountain chains we have in Italy. And once the temperature started to increase, the snow melt, and basically you will have more water available. This happens in springtime and summertime, so you can produce more energy from hydropower plant. If you change the scale, so you don't consider the gigawatt hour, but the production in per unit of the maximum value. Okay, so I take this maximum value here and I divide the other value by this maximum value. So I have the per unit of the max production. What happens? It happens that we end up with this very nice chart, in which you can see that basically the hydro and PV are correlated each other, but are in opposition, let's say, with the wind. Okay, so when the wind is high, hydro and PV are low. When the wind is low, hydro and PV is high. So what's the conclusion of this? The conclusion of this is that it is very useful to have if we want to move to a 100% REST power system, it will be useful to have a mix of hydro, PV, and wind. So we have to be able not to put all the money in one of these technologies, but basically to have a mix of them. So that in winter time I have less water and less solar radiation, but I can believe on wind. Vice versa, in summertime, since I have maybe enough PV and hydro, I can also do not have wind. Okay. Vice versa, if you build up a power system with just the PV, look, you will have a very high production in summer, but that maybe not enough production in winter time. Okay, this is a very important concept you have to keep in mind. The best approach of having 100% power system is to have a mix of those technologies: hydro, PV, wind, also biomass, geothermal. So don't try to push just one of the technologies. Just try to incentivize all together. Okay. So here was just to show you the trend of the RES. So look here, in wintertime, wind produces more than photovoltaic. But if you go to summertime, look, the photovoltaic produce more than wind. And wind is also producing less than biomass, okay? So basically, wind is good in wintertime. While the solar radiation, look, the production from PV increases in springtime, and then it remains stable in summertime, and then it decreases in autumn and wintertime. Okay, so summertime and springtime are good for PV, wind. Of course, it depends where you install wind and PV. But for the case of Italy, this is the situation. Okay, so here it is just to highlight you again the difference between programmable and non-programmable power plants. Okay, so let's consider to have this load profile for a day to be covered. Okay, the 3rd of February 2020. So the demand is requiring with this load profile. On the right, you see the mix of generation used for following the load. Okay, look, it is immediately clear that the thermal power plants, which is the one in red, has more or less the same shape, right, of the load. Why? Because basically is a programmable source. So I get all the other sources like PV, and look, also the hydro production is following the load. Okay, but what about the solar radiation? The solar radiation is not following the load. So the production from PV, it is just given as it is from the power system. But if I want to follow the two peaks of the load, I have to change the production of the programmable thermal and hydro power plants. Okay, that's more clear if we look just at the production from RES. Okay, so this is for the given day, the 3rd of February, the production, but just of the renewable energy sources. Okay, so basically, look, for the PV, you have the classical bell curve. Okay, which is taken as given by the solar radiation. Okay, then okay, here you have the biomass, which is quite constant, and here you have the geothermal, which is quite constant. So basically you have the solar radiation as given. The wind, look, the wind is producing more or less the same, which is the only RES that is changing the production to follow the load. Is the hydropower plants, right? So basically wind, geothermal, biomass, and PV are taken as given, okay, based on wind and solar, while the hydropower plants are controlled because are programmable power plants and are programmed, are scheduled in a way that we are trying to cover as better as possible the load profile. So the load profile is given, and this is the result of dispatching. Result of dispatching power plants. Okay, so with the power plants, we have always to cover the load. You can imagine is that if the load is given and also the generation, PV, wind, etc. is given, it is not very easy to match the load and the generation. Okay, the only way is to have some programmable power plants like thermal and hydro that make the match between load and generation. If you think to exclude completely thermal and hydro, you will end up with a power system which is for sure right now unstable, because you cannot satisfy your load, because you cannot change the generation to follow the load. That's the idea. I told you this in many different ways because I want to be sure that this concept is quite clear. And basically, you can see this very clear from here. So what happened? It happens that in 2018, on April the 1st, at 2 p.m., when basically I have production from PV, hourly, so if I consider 2 p.m. of the 1st of April 2018, 82% of the load was covered by RES. Okay. So basically, I'm very, very happy. Okay. But as I told you at the beginning, you don't have to satisfy. So here we are very close to have a 100% RES power system, right? But as I told you at the beginning, you don't have to have the covering of the load with RES just for 1 hour in a year, but for the all hours. In fact, if we consider a day, an entire day, May the 13th, I was able to cover just 72%, right? And if I enlarge my time frame to a monthly, May, I was able to cover just 46%. Okay. So looking at the best hour, it seems that we are very close to have 100% RES power system. But that's not the case, because if you go down, and of course, if you consider the yearly, probably this percentage is much less. But if you go down, or if you make bigger the time frame, the percentage is reducing. So we are not very close to have 100% RES power system. That's the conclusion. Okay. This is another important thing that you or all us electrical engineering and engineering in general have to have in mind. Okay. So, but first of all, let's have a look first on the left side chart. In the left side, you have the RES install capacity. Okay. Okay, so the megawatt of RES installed in Italy from 2003 to 2017. Okay. So the RES installed capacity, if you consider, for instance, a household, at least here in Italy, we install normally a PV power plants of 3 kilowatt peak power. Okay. So you install a capacity of 3 kilowatt of power. Okay. This is the capacity. Okay. Here I just want to highlight you what happens in 2010, starting from 2010 in Italy. We have a very huge PV booming. Okay, look, the PV power install increases a lot, and it reaches more or less the power install of hydro. Okay, and also the wind, look, increased. Okay. So finally, the power install increases a lot, starting from more or less 2010 in Italy. Okay. So starting from 2010 in Italy, we increase a lot the install capacity. But the install capacity is power, right? What about instead the electricity production? So the energy. That's another story. Did you see something strange if you compare the left chart and the right chart? Please help me in highlighting something strange or something that you don't understand maybe. Or just let me ask you another thing. If I tell you this on my household, I install 3 kilowatt power of PV, which would be your question to me? I say, yeah, okay, I decided to install 3 kilowatt of power. Which would be your additional question to me? Do you have any idea? Or you just take this information as, let's say, satisfactory? Okay, my friend installed 3 kilowatt power on his rooftop. I'm happy. Do you think it's enough to have this information or not? Some ideas? So let me ask you another thing, but here I want your answer. I take the same 3 kV power plant, but I install all the module flip, okay? So with the solar cells looking to the rooftop, not on the other side, okay? So I mounted my PV power plants wrong, okay? So the solar cells are not looking to the sky, but to the rooftop. And I say, okay, I installed 3 kilowatt peak power plant. Option 1 and option 2 are the same or not? I still install 3 kilowatt of power, but are the same or not? What do you think? So which is the energy? produced from here and which is the energy produced from here. So guys, don't be shy. Please help me. Which is the energy produced for the power plant number 2? Is there any more? Anyone wants to answer? Someone has an idea? Can you hear me, guys? Hear me, guys? Guys, can you hear me?
It's clear.
Okay, okay. So you hear me? Okay. So basically, if I install the PV power plants in the wrong way, my energy produced will be 0, right? While here I will have a certain amount of energy APV, okay? So even if I have the same power installed, I could have a very different energy production, okay? And that's what you can see also from here. Look, this is the installed capacity of PV and hydro is more or less the same. But look, the energy produced from hydro is much higher than the energy produced from PV. Okay? But what's the reason of that? The reason of that basically is what is called the full load hours. Okay? So the rest, okay, here there is a mistake. The renewable energy sources have a full load hours, which is significantly different. What does it mean, significantly different? If you consider a geothermal power plant, okay, so those are the Italian data. So if you consider a geothermal power, all the geothermal power plants in Italy, and you divide the energy, the yearly energy produced by the installed capacity, okay, so you divided gigawatt hour by gigawatt, you end up with what is called the full load hours, okay, which in this case is 7,627 over the all hours of the year, 8,760. So basically, a geothermal power plant has a full load hours, which is 87% of the all hours of the year. So its production, as we seen already, is quite stable. Okay, so the geothermal power plants are producing almost the same for the all hours of the day. The bioenergy instead, if you still divide it gigawatt hour by gigawatt, just produce for half. So the bioenergy power plants are producing at the full capacity just for 54% of the hours. Okay, but what about our, let's say, the other rest, hydro, wind, and solar? Having a look to the solar, we see that if we divided the energy by the power installed, we end up with the number of hours at the full load, which is 1,238 hours. So just 40% of the 860. Okay. So basically, if your friend told you that it installed 3 kilowatt power of PV, your additional question would be, yes, but which are the full load hours of your power plant? Okay, my full load hours are more or less 1,200 hours. Okay, based on these two information, okay, I know that my PV power plants will produce 3,600 kilowatt hour a year. Okay. This is the information, the most important information. It is not the power, it is the energy. Okay. When you hear some news or in television, we will install 10 gigawatt more of power, it doesn't make any sense. Because if we come back to this example here, even if I install 3 kilowatt of power, that's not correspond of having energy. I just have something installed. But what it is important is how much energy I can get from that power plant. And from here, basically you see that hydro, wind, but especially solar, they have a very low full load hours. Okay. So basically here and if you consider all nowadays in Italy, okay, if I consider all the rest, the full load hours of all the rest is just 22% of the all hours. Okay, so basically just for 22% of the hours I have the rest producing at the installed capacity. In all the other hours are producing less than the installed capacity. Okay. Here I just made a very easy computation. If I consider the yearly consumption of Italy, which is 320 terawatt hour, we will need to install, to cover this, okay, to produce this energy. It is just a very easy computation, but just to give you some numbers, if I want to cover this energy just with RES, I would need 175 gigawatt. Okay, because if you multiply 175 by the number of equivalent full load hours, you end up with the energy. Okay, and this value here is 3 times more the current power installed for RES. Okay, so even if we would like to cover all the load of Italy with RES, we should have to install 3 times the power we already have now. okay, which is not very easy. Moreover, going from traditional power plant to RES, okay, it will need 50% more of the installed capacity, okay, because basically here you don't have, but a thermal power plant, so from coal or from gas, could have a number of full load hours very close to the geothermal one, okay? Because if I get fuel, I get energy. I'm here that I'm controlling the production. So basically, if I want to just rely on RES, I have to double the installed capacity we have right now from thermal power plants. Okay, so here it is something like you have a Ferrari car or a Lamborghini or whatever, a high-level car with a very big engine, but you have the fuel, okay? So you have a very big and nice car, but you have the fuel just for using this car 22% of the time in a year, okay? That's not very efficient, I would say. And as a consequence of RES and their impact on thermal power plant, here you could see from 2012 to 2018, which is the available reserve capacity at the peak load, okay? So you have to consider the peak load you have in a year and basically look at the reserve margins, okay? So the power that you have available at that time to cover maybe the lack of the RES production. And from here, you see that this reserve capacity, which is needed for the reliability of the power system, decreases from 2012 to 2018. So basically, what is happening that the power system is becoming weaker and weaker, because if I don't have a reserve capacity, if for a certain reason I lose production from wind and from RES just because maybe of the weather, I'm not able to recover the energy that I forecasted would be produced from RES using traditional power plants. Okay, so this is a trend a little bit dangerous, okay, because I'm shifting out from the power system the traditional thermal power plants, which are programmable. And this is different than RES, which are not programmable, okay? So here it is just to say that RES are good to cover the peak load, okay? So the peak load in 2016 in Italy was in summertime, and look, there was a nice contribution of the photovoltaics, the same in 2020. So PV is good for, since the peak load is in summertime, PV is good for covering the peak load. But look, if we look at the valley load, what happens? That I don't have the photovoltaics because the valley load is during night hours, 4 in the morning. So the photovoltaic is 0. So I have to come back to traditional power plants. Okay, so most of the energy is from traditional power plants, while during daily light hours in summertime, I can rely also on RES. Okay.
Alessandro,
Yes.
I have idea like this.
Yes.
So you speak about 3 hours more or less, right?
Yeah.
So too much for you.
Okay. No. That was the question I would like also to ask you, if we can stop here or.
Yeah. In Vietnam now it's around 6 p.m.
Okay. Yeah. I think it's time to go for aperitivo probably.
Yeah. and also for you to take a breath.
Yeah. It's almost time for lunch even here.
Okay. So
Yes.
let's do
come
that.
back.
Yeah.
No. Please. Go away.
So we today I think we have more than 3 hours. It's okay.
Yeah.
It's so very good. It's very good. And we could stop here and then we meet next Sunday.
Okay,
And
that's perfect.
and before stopping, we should say we will start at what time you would like to start?
No, that's from my side. It's good also to start at 8. Don't worry, I can manage it.
Okay, so in
So
Vietnam.
we come back to the original schedule, but with the right hour, let's say.
Okay, that's good.
Okay. Okay. So next Sunday we will start at 8, so that we can finish 1 hour before today, let's say, more or less.
Yeah. Let me speak Vietnamese.
Yeah, of course.
Em sinh viên là chắc là giờ các em cũng tới giờ chúng ta đi nghỉ ngơi ăn tối rồi hả? Thì những cái phần mà giáo sư Alessandro trình bày cho các em á, thì nó cũng rất tốt rồi. Nó càng về sau thì nó càng kiến thức nó càng sâu hơn. Thì chúng ta cứ nâng dần lên như vậy thì nó rất tốt. Thì giờ thì chắc cũng tới lúc các em đi ăn tối rồi nghỉ ngơi rồi. Nên bữa sau thì chúng ta sẽ bắt đầu vào lúc 2 giờ và giáo sư Alessandro sẽ tập trung vào những cái nội dung chính. Còn những nội dung mà trong slide mà nó có mà thấy rồi thì các em chịu khó đọc và chúng ta trao đổi thì nó sẽ hay hơn. Đồng ý không các em?
Dạ được thầy ạ.
Còn em Huân mới nãy record thì chúng ta sau đó chúng ta tắt cái record, sau khi kết thúc tắt cái record để sau đó các bạn cần nghe lại chúng ta nghe ha.
Professor Alessandro.
Yeah.
Thank you so much, Professor. I'm sorry. My vocabulary is so limited, so I can't talking anymore. And answer your question. I'm sorry.
Don't worry.
Yes. Thank you.
Don't worry.
Thank you. Anymore.
No, thank you.
You shared for today.
Thank you to all of you. I hope you catch something that you didn't see in other lectures. I think so, because I try to focus more on the power system. And the next lecture I will go into more details of the impacts of RES on transmission and distribution. Okay, so you will be much more satisfied, I'm sure.
Yeah. Okay. Thank you. Thank you, Professor.
Thank you. Thank you.
Okay. Thank you very much, Alessandro Bosisio.
Thank you, Lee. See you next week and enjoy the rest of the Sunday.
Okay, thank you very much.
Okay. Bye-bye to everyone and see you next week.
Okay,
Yes,
bye-bye.
bye. See you next time.
Next time. Bye-bye. Bye-bye.